So our next session is on heat transfer materials. So it's this is a totally new technology as opposed to thermal energy storage, which has been around longer than I have. So Jeffrey Ihnen is going to present. He's the CEO of Michaels Energy. Jeff started on the ground floor with Michaels in January 1996, doing energy audits and feasibility studies. He worked his way into managing the energy efficiency practices, and for the last several years, the entire company. Jeff's current responsibilities as CEO include program, evaluation, proposal, and sales strategy, as well as discovering the next big thing. Jeff earned a bachelor's in mechanical from South Dakota State University. He spent 4.5 years in the Naval Nuclear Propulsion Program, earning a master's of nuclear engineering. Before joining Michaels, Jeff earned a bachelor's of science in mechanical engineering from the University of Wisconsin-Madison. Let's see what you got, Jeff.
Good morning or good afternoon, everyone. This is Jeff Ihnen, CEO with Michaels Energy. Today, we're going to talk about thermal energy storage with phase change materials. We're going to look at a lot of different phase change materials. First, I should give you a background. I'm a mechanical engineer by training. I'm not a phase change expert, but I have 25 years of experience in energy efficiency and demand management. So I'm very interested in phase change materials for saving energy and shifting load from on-peak to off-peak periods, or soaking up extra energy production for spaces that have a lot of renewable energy. First of all, a little bit of a review for phase change materials. What we want to do is store a lot of energy, which is on the horizontal axis here, which is the value. And what we don't want is a lot of temperature change for that energy storage, which is the whole point of PCM. So we want to store a lot of energy and not change the temperature much, because products and people don't like temperature fluctuations. So the outline we're going to look at today is phase change material characteristics, some basics on that, types of PCMs that I looked at for this study, applications and considerations, and some results of some tests that are available, and then finally some conclusions that I came to in all of this research I did. PCM characteristics. So these are things that, when I stop and think about it, are very important. So first of all, we have the latent heat of fusion of the material. Of course, that's the whole purpose of the phase change material. We want to store a lot of heat per unit mass of material, and water happens to be pure water happens to be the highest latent heat of fusion, with about 170 BTUs per pound mass. And everything else that I looked at is less than that, and we'll look at that in a couple slides. Next is the sharpness of latent heat. We want the material to freeze and melt at a smallest range of temperature possible. Again, pure water is the best because it freezes at exactly 32 degrees. Other PCMs freeze and melt over some temperature range, depending on the material. It can be up to 2 or 3 or more degrees Fahrenheit or Celsius. And then there's the melting and freezing proximity. Some materials melt at a higher temperature than they freeze. That again is not desirable. We want the temperature of melting and freezing to be as close as possible, because we don't want the temperature fluctuation. Stability, of course, is how long does the material last? We want it to last for years. And then finally, there's containment systems. Some of these phase change materials are very corrosive, so metals aren't good. Metal's a good conductor of heat, but it's obviously prone to corrosion. And plastics are another one largely used for these corrosive materials, and they can have problems with hydrocarbon based or organic based, which are hydrocarbons, organic based materials, because that you got to have the right plastic or it can react with the material. So I looked at 4 families of PCMs, and I'm mainly interested in the temperature range of freezing for food storage and space conditioning for people or equipment. There's phase change materials that go from well below 0 degrees Fahrenheit to in the 2,000 degrees. I'm mainly interested in space conditioning for equipment and refrigeration and frozen food storage. So there's salt waters, or hydrated salts, organics, and then plant-based, which is a subset of the organics, which, basically, again, hydrocarbon chains. So we'll look at these and talk about them on the next slide. So here are the freeze points and the latent heat of fusion for these various materials. Let's start with the salt water mix. So salts and water, of course, when you add salt to water, it depresses the freezing point, which is why we put salt on the roads up here in Wisconsin in the wintertime to melt the snow and ice. So we start off with pure water here, which is a latent heat of 170 BTU per pound, which I think I mentioned already. And as we add more salts, it depresses the latent heat capacity of the mixture. And you notice that there are discrete points of freezing point versus latent heat. And the reason for that is there's precise mixture of salts and concentration of salts with the water to get the entire solution to freeze at one temperature, which is called the eutectic freeze point. Otherwise, if you remember phase change diagrams for mechanical engineers looking at, steels and anything that freezes or turns, that crystallizes, we don't want the material to freeze at one temperature, and then the water freezes out of solution, and then the solution gets more concentrated, and then finally the whole thing freezes. So that ends up giving you a range of temperatures again, and we don't want that. So they've engineered these precise mixtures of salt and water to freeze at exactly one temperature, which is the eutectic temperature. And so the salt water mixtures are excellent for phase change materials. And then we move into hydrated salts. And so to me, again, I'm not a phase change material expert. To me, the hydrated salts, rather than mixing salt with water, the water is actually absorbed into the salt and freezes at various temperatures, discrete temperatures with various specific latent heat capacities, and we can see that these are a lot lower, but these are these are in the temperature range of occupied spaces, right? So in the 60 to 100 degrees, or and as shown on the chart here. And then we have the gray bar, which is the organics, the gray curve or line, which is the organics, and this includes petroleum-based products, waxes, paraffins, oils. A lot of stuff melts and freezes at different temperatures. And basically, the difference in these materials is the length of the hydrocarbon chain. So the longer the hydrocarbon chain, the higher the melting point. And the challenge with the hydrocarbons is they're usually not pure. You get different hydrocarbons mixed in with, say, your paraffin waxes. And so again, different hydrocarbon chains mixed together produce a melting point over a range of temperatures, which is undesirable. So it gets really expensive sometimes to get a pure enough hydrocarbon to have a precise melting point. So why look at this stuff? I like to know about the material and how it works so that I know how to apply it in a situation, so I know what I'm getting into and the things that I need to design for and consider. So look at some applications. So this is your basic thermal energy storage that's been around for decades. We use glycol and chilled water, or glycol water solution to freeze ice in the storage tank, and then use it off peak. You're charging more charging off peak and then using the ice on peak, I should say, correct myself. The disadvantage of these systems is rather than making water at the temperature the load needs of, say, 35 to 45 degrees Fahrenheit, we need to make glycol water at 25 degrees to freeze the ice in the tank. And that, of course, requires more compressor lift, which requires more energy. In addition to that, the glycol water mixture impedes heat transfer, which increases the lift a little bit more, and plus it's more viscous, which requires more pumping energy. So we can shift load with this technology, but it costs more in energy because of the compressor lift and the added pumping energy. So it's not the best from that perspective. But for space conditioning, it's probably going to be around for a long time. Then I looked at saltwater PCMs. So as you can see, these packets, resemble the packets you put in, your cooler to go for picnics or parties, or, have it in your, transport things in your trunk for hours at a time. And so again, these are mixtures of salts and waters put in these containers, and they're stored up out of sight, out of mind. And so they're not invasive. You don't have to shut down anything. The advantages include they freeze and thaw at the temperature of the space. Unlike the ice storage that we just looked at, where you have to make 25-degree water versus 40-degree water, here you're just making it a little bit cooler to freeze the material when you're charging the material or freezing it. And then it melts at a temperature that's almost the same. So it works great for that. And it also saves energy by shifting cooling loads from the hot middle part of the day in most cases to overnight when the cooling conditions are more conducive. The outdoor temperature's cooler, which makes your compressors run at a lower head pressure for most of these ammonia systems anyway, and even some of the Freon-based systems, which is shown on the left. The other thing is it allows the equipment to run at a fuller load. So commercial industrial refrigeration, or at least industrial refrigeration, runs more efficiently when it's more fully loaded, whether the compressors have part loading due to cylinder unloading for reciprocating compressors, or rotor shortening for screw compressors, or even variable freak drives. The equipment and the systems run more efficiently when it's more fully loaded. And so, of course, we're shifting load from on peak to off peak, and we're saving energy at the same time, and so that results in a lot of dollar savings. So the tests that I looked at for salt water PCMs for frozen food were about 25 to 40% energy savings, which is a lot. Again, it's due to shifting to cooler periods, which allows to reduce head pressure and run at full capacity. The demand savings here is understated, I would say, because what they showed was, here's the peak demand before, here's the demand after. It didn't matter when it happened. They just took the difference in those two. When the reality is, if you want to use this for load shifting, to shift out of peak periods, or whether you want to use it for demand response, you can get almost 100% demand reduction based on, of course, on how much material you use and how long that period is. It can easily last 4 to 6 hours, probably. So it depends on the tariff, and it depends on the demand response need. It can be a lot of demand savings with this as well. The next thing I looked at is a bio PCM and a telecommunications application. So this is telecommunications hut or shelter, they call it, 750 square feet. So this includes a bio PCM blanket, and we'll look at what we'll see what a blanket looks at in a couple slides ahead. But the blanket is installed in these panels, which are attached to the wall and have direct contact with the space air, which works very well. Like the freezer condition, this is a really good application for PCMs because the equipment doesn't care about a few degrees of temperature change. In this case, the space was 78 degrees. It probably needs to be cooled to 75 degrees to freeze the PCM when it needs to be frozen or charged. And then it's melted maybe at 80 degrees. The equipment doesn't care whether it's 80 degrees or 75 degrees in the space. So it's a great application for that. The energy savings for these applications were 15 to 25%. There was no mention of demand savings, probably because these are really small facilities and there's no demand component to their bill. But they were looking at this for hundreds of these shelters across the country. Another really good application. So next we move into PCMs for commercial buildings where things get a lot more challenging. So the options that I looked at are PCM blankets and walls. We'll look at that. We already looked at PCM blankets and panels on the telecom application a couple slides ago. There's a study with hydrated salts in wall cavities. And then finally, I look at encapsulated paraffins mixed in with cellulose insulation inside a wall. So we'll look at each of those. So one application I looked at was PCM blankets. I said we would see what a PCM blanket looks like, the stuff that gets installed in those panels. Here is an image of the PCM blanket, which shows little packets of phase change material compressed in this plastic and other material. Then it's adhered to the framing, in this case metal studs, and then the gypsum board will go over the outside of that. Now, as shown, this is an application on the interior partition of the facility. The challenge to me here is you're going to put a gypsum board on top of that. And so gypsum board, of course, isn't a great insulator, but it does provide some insulation. And the materials behind that, and in order for the material to work, to freeze and thaw, which is what we need to do for PCM, you've got to get enough heat transfer to that. It's got to get warm enough during the day to melt the material. Then at night, it needs to be cooled enough to charge it or freeze it. And that is going to result in a pretty good temperature swing, I believe. And it requires a lot of testing. So all they looked at here was, how does the PCM space perform in a test case versus a control space? So it's kind of like an A/B test, in other words. So all they looked at was, how does the PCM moderate temperature swings in the test versus the base case? And the results weren't that impressive. The temperature swings were almost as great in the test case as it was in the control case. And I wasn't seeing much of temperature moderation where the material was melting either. So, I think this is just a demonstration, and there was no energy impact available for this particular test. The next one similarly was to demonstrate the temperature moderating effect of using hydrated salts in a wall cavity. This study was done in Germany. I had to go far and wide to find test results for space conditioning examples. And here, as you can see in the wall, we have an A/B test setup with part of the half the facility has PCMs installed in the wall cavity, and the other half does not. So we're comparing PCM in wall cavity versus open wall cavities. And here we can see again that the packets look like the freezer packs that you use in coolers. So they just installed two layers of these in the wall cavity in the test case, and then on the control side there was nothing apparently. And I don't even know if they put gypsum board over these or not. But so this shows the results: the outdoor air temperature in green, The blue line is the control, and then the red is the test case with the PCM. In this case, we can definitely see that the temperature is moderated whether the material is freezing or not, and that's just due to the thermal mass. I mean, the material, whether it changes phase or not, adds mass to the wall and is going to dampen the temperature fluctuation from day to night. But what we can also see is this material melts between 21 and 23 degrees C, and you can see what really works here in that 21 to 23 degrees C range, where it really holds the space cool when it varies around that temperature. So again, there's no energy savings results for this. It was just a test to see how it moderates temperature over quite a few days. And then finally, a bonus, what I'm calling a bonus. I didn't include this in my paper. There is a paper for this. I'd welcome everyone to take a look at that. This was a study done by Oak Ridge National Lab where they used encapsulated PCM material, which is a hydrocarbon or a organic PCM, mixed it in with cellulose, and they looked at it in different configurations, whether they used the cellulose and PCM material sandwiched against the gypsum board or against the outside sheathing or in between with just pure insulation on either side. And then they also did one with the cellulose and PCM throughout the full cavity. The results are shown over here on this chart. And what I take from this is probably on the south and west facing facades for this test, they probably had phase change. So there was enough heat gain, solar and temperature, solar mainly, I guess, heat gain such that the material changed phases and they got more energy savings from the south and the west walls than they got from the north and the east walls. Again, it adds some thermal mass to the wall, which always saves some energy. But so I penciled this out, and basically it comes out to, if I look at a 100 by 100 square foot, 100 by 100 building, which is 10,000 square feet, the savings are only 100 kWh for this type of facility, which is 0.01 kWh per square foot. So it's a challenge to get energy savings with PCMs in wall materials, is what I conclude. And speaking of conclusions, my conclusions are from my research is that PCMs are great when there's direct contact of the PCM and the space. So whether it's conditioned space for occupants, occupied for people or equipment or frozen foods, it's best to have the material in direct contact with that space being conditioned so it can transfer heat without a lot of temperature swing. PCMs will have challenges cooling or conditioning in occupied spaces, again, because it needs to freeze and melt over a temperature range that is typically not, it's not attractive for building occupants. And one thing that I forgot to mention is that, PCM, in order to freeze it in when it's installed in or even in a panel or in a wall, you may have to subcool the space to freeze the material to coast through the day, and that may make the space too cool for occupancy first thing in the morning. So you don't want to have to freeze the material overnight and then puff in some heat in the morning because it's too cold for occupants. That's another challenge with that application. And PCMs installed in wall structures is going to require a lot of testing because the heat transfer characteristics is just very complex, and I think it's going to require testing to see what works and what doesn't work, both with the material and where it is in the wall and so forth. So that is all I have. Again, my name's Jeff Ihnen. I love to get questions from people. So there's my email address. Feel free to follow up with me anytime. and enjoy the rest of the conference.
All right. Jeff, thank you. That was good. We've got a lot of questions, and we have about 14 minutes to answer them. So let's see what we can do. My first question, what types of containers are used to store salt water? And what's the lifetime of these containers given the salt water is corrosive?
The containers for the salt water are essentially like the material, the plastic material that's used in your cooler ice packs, and their lifetime is very long, 20 years plus.
Okay, that'll work. So these small saltwater systems, how available are they? And what is the smallest practical application, for example, in terms of tons?
Tons. So they're modular, as shown on one of the images in the presentation, and they're probably I'd say like 24 inches long, an inch thick, and so they could work for really small applications as long as there's space for it in the facility.
Do you have some sort of measurement number? I mean, maybe it sounds like you don't use tons. Do you use something? What do you use to say how big, what the capacity of this unit is?
I think they're rated in kW. Like ton hours. Ton hours probably is more appropriate. Yep.
Okay. With the 25 to 40% kilowatt hour savings, what else besides ambient temperature, night-day difference contributed to this high savings number?
I thought about that. The one is the air conditioning or refrigeration system runs at a fuller load. So air conditioning systems, or I should say refrigeration systems, work most efficiently, or compressors work most efficiently when fully loaded, whether it's a recip compressor where cylinders are unloaded, or whether it's a variable speed drive recip or screw or screw compressor or whatever the case. If they can run at fully loaded, it's more efficient.
Okay. For the installations with the PCM in a wall cavity, do they just absorb from and release to the room, or is there piping, cooling, or some piping going and warming the materials, or is it just the room going?
In the cases that I've seen, they've been completely passive. So no piping, they're just in the walls. As I said mentioned in the presentation and in the paper, there is a paper that I wrote for this. It's a challenge to have PCM built in a wall, especially if it's internal wall or partition, because you need to cycle the temperature between charging, which is freezing the material. At night, you need to cool it, of course, colder than the freezing temperature of the material, which brings it down to a temperature of say 68 degrees or 69 degrees, and then during the day the temperature needs to come up so that the material melts, and so that's a temperature swing. It makes it a challenge for the material on an internal wall. They also install it. They've also done studies where they install it on the exterior wall. And essentially there, you're just adding like thermal mass. So you could, build a building out of concrete masonry units and brick and accomplish the same thing. So to me, it's not the greatest application for walls. As I mentioned in the paper for sure, that it's best to have the material exposed to the space, as close to the space as in the space if possible.
Okay, so this is something we were speaking about just recently or in the green room, and that was I worked on a project where they put this phase change material above the suspended ceiling. They thought that this was going to dramatically reduce cooling energy for cooling the space. It's just an office building. What do you think of that?
I was skeptical of that when I first evaluated that just from a heat transfer perspective. It's above a ceiling tile. A ceiling tile has an R value of about 1.5. So you've got an insulating effect there. Again, for phase change material to work, it needs to cycle from solid to liquid, and so you need that temperature change from charging to discharging, and it becomes difficult that way. Plus, you're above the ceiling in the ceiling cavity space. What is going on up there? It might be a plenum return for an air handling system, or it may be dead space, and it may not be doing anything. I mean, it's really hard to evaluate. For instance, what effect like lighting fixtures have on the space heating and cooling loads. So I would be skeptical. I would not install it above ceiling tiles for those reasons.
So I was skeptical in the past about this same thing, and because generally temperature control systems will maintain the zone temperature within a pretty tight band, maybe a degree or 2 degrees. They keep it at a certain set point. So as you said, the phase change material can't melt and recharge because it doesn't really leave the band because of the control system. But what they said, this company said in response was, well, no, you put this in and then you change the control system so that now you have a wider band. So now that the phase change material can keep the zone, within these temperature confines less than the, and then once it's used up, then the control system or the HVAC system will then adjust. Does that make sense?
Yeah,
I don't know if it works, but
we do quite a bit of retrocommissioning, and one of the things we emphasize when we do retrocommissioning is the Hippocratic Oath. I think it's called "Do no harm," and you don't want to change the space conditions because if you do a project and then the occupants complain, well, that project is not going to last.
Right. Good answer. Okay, what about PCM in ductwork or using the wall cavity as a plenum so you can reduce the insulating effect of the wall board?
I think that's an excellent idea. In fact, the last presentation with thermal ice storage, when there were questions on the DX, that's exactly what I was thinking, that you could put phase change material in, say, heck, it could be in an insulated box, like in a home basement or whatever. And you just, the air flows over that and it charges at night. I guess the problem was you would overcool. But I think that could still work. I think that's I think that could still work. I need to think through that, but I think that's a great idea.
How about if you used it on a flat plate heat exchanger for tower-free cooling? Would that work?
For what cooling?
Tower-free cooling, economizer where you use the cooling tower instead of a chiller to cool.
Yep, I think that could work. You mean, it depends on the application. But again, I think anytime you can get the fluid in almost direct contact with the material, you've got something to work with.
So this would be on, like, for example, lining the flat plate heat exchanger itself. So,
okay,
it might work. I don't know. I was just curious what you know.
Yeah.
If you thought about it.
I haven't thought about that, but.
Okay, do you have condensation with PCM melting?
That is a good question. I would say, like in the case of the freezer spaces, probably not, because you're driving that temperature down over a long period of time. And if you want to dehumidify air, that's what you do. You run your cooling system full out for a period of time, and then you're drying out the air. Now, if you've got a lot of forklifts coming and going, and you got a lot of infiltration, then yeah, I imagine you might have condensation issues. That's a good question.
Okay. So how would you compare, or can you compare, phase change materials to thermal energy storage and battery storage? Does that even make sense to try to compare them?
Sure. Because some of the phase change materials, as I mentioned earlier, are can be measured in kW or ton hours or kWh. So I got to make sure I answer your question. The good thing with the thing that I haven't seen happen yet in my research with the phase change materials is I haven't seen it used for a wide range of temperatures. So in other words, like in say a convenience store, refrigerated case where they have storage in back, you pull the door open and you grab your sodas or milk or eggs or, whatever. I think PCMs could work in there. The saltwater PCMs are for freezing, below freezing 32 Fahrenheit only, but the bio PCMs or the organic PCMs and even the hydrated salt PCMs could be used in those refrigerated cases, I think, quite effectively. And so the effects are basically the same as a battery, cycling through a peak period.
Do you have any final comments? Is there anything you want to add to your presentation that you
I think there's a lot of potential for this technology, from especially unoccupied spaces or spaces that are not so sensitive to temperature like human occupied spaces. So freezers, refrigerators, telecom spaces, data centers. But also, we talked a little bit about using them in direct contact for those occupied spaces where, it's being directly cooled by air, or I should say cycled, frozen and melted by airflow. I think that's a potential.
Here's a question. So in terms of life cycle cost, I know this is general, but do phase change materials, do they have a better life cycle cost than just getting a more efficient DX unit or chiller? I know that's really vague, not vague, but it depends, but just in general, can you give us some indication?
I would say so. I would say that it's probably going to be cost effective. Now, how does it compare to getting something more efficient? The cost effectiveness of doing efficiency largely depends on what you have in the baseline case, right? Mm-hmm. So I think the phase change materials will be cost effective in many cases, even with very efficient equipment, because we have what I call the 1/X thing, which is 1 over efficiency, and you get the diminishing returns as efficiency increases and increases. You can double the efficiency and you just get less and less savings from that. So I think phase change materials can always be cost effective.
That's good. All right. Well, we've made it through our question session. Thanks a lot. I appreciate your time, Jeff. That was a good presentation.
Thank you.
We're ready to move on to our next one. So our next presentation is on pumped pumped water storage. I think that's what we call it. Actually, I'm the one giving the presentation. I'm